Hi, welcome back. This is still Ken, and we're still on our course on mechanics, and this is the last part of lesson 3 in motion in 2 or 3 dimensions. In this video, we're going to discuss about uniform circular motion. We begin with our study on uniform circular motion. When a body or a particle is said to be in uniform circular motion, the body or the particle moves along a curved path, and the direction of its velocity changes. However, for uniform circular motion, the speed of the body or the particle is constant. The particle must have then a component of acceleration perpendicular to the path, even if its speed is constant. When a particle moves in a circle with constant speed, the motion is called uniform circular motion. Some examples of systems or bodies undergoing uniform circular motion are the following. You have a car moving in a curved path, you have your Ferris wheel, or you have your satellite revolving around the Earth. For uniform circular motion, there is no component of the acceleration parallel, or other term for parallel is tangent to the path. Otherwise, the speed will also change. And the acceleration vector is perpendicular or normal to the path and hence directed inward and never outward towards the center of the path, which causes the direction of the velocity to change without changing its speed. Look at the figure below. So this is for a car speeding up along a circular path. This green line here represents the vector velocity of the car speeding up along the circular path. Now, since this car is moving around this circle here, you'll see that the direction of the car changes. Now, since the velocity is a vector quantity, again, it has both magnitude and direction. But we have stated earlier that for uniform circular motion, only the speed of the particle is constant. So there is no change in the magnitude of the velocity. However, since it changes its direction as it moves around the circular path here, the velocity changes. Now, since the velocity changes, there should be an acceleration of the body. However, this acceleration has the direction which is directed inwards to the path or towards the center of the path. And this acceleration is perpendicular to path at any point. Like say for example at this point here, perpendicular or normal to this path at 90 degrees is this one here. And this one is what causes the particle to move in a circle. And there should be no component of the acceleration that is parallel to the path. Like say for example this one here. We should not have a component of the acceleration which is parallel to this path here. If you see here, we have a component of the acceleration which is perpendicular to the path and also parallel to the path. And here, the component of the acceleration parallel to the path is in the same direction with the velocity. That means here, for this example, the car is speeding up along a circular path. It moves faster and faster. For figure B, the car is slowing down along a circular path. So in here, if you're going to look at the acceleration, your acceleration has a component perpendicular to the path, and it also has a component which is parallel to the path but goes in the opposite direction of the velocity. So here, this is not again a uniform circular motion since we have a component of the acceleration which is parallel to the path, and for this case here, the velocity vector and the acceleration vector, which is tangent to the path, goes to different directions. They are anti-parallel. So for this case, the car is slowing down to a stop. Lastly, on figure C, we have here the acceleration only, the acceleration vector, which is only perpendicular to the path. Again, this is at 90 degrees to the path or normal to the path. So for this case here, the acceleration is exactly perpendicular to the velocity and no parallel component. Thus, of the three figures here, Only this figure, which is figure C, undergoes uniform circular motion. Again, for a uniform circular motion, there should be a component of the acceleration parallel to the path, and the acceleration component or the acceleration vector is perpendicular to the path and also directed inwards, like for figure C here. For uniform circular motion, the instantaneous acceleration always points towards the center of the circle, and this is sometimes called the centripetal acceleration. The magnitude of this acceleration, which is the radial acceleration, is equal to v squared over r, where your v is equal to the speed and r is equal to the radius of the circle. We can also write this equation for your radial acceleration in terms of the period t, where the period t is the time for one revolution. And writing the equation in terms of t, we have the radial acceleration is equal to 4 pi squared times r over t squared. As a short recap, in this video, we have discussed about motion in 2 or 3 dimensions. We have discussed about the position, the velocity, and the acceleration vectors. And we have discussed a special case of the motion in 2 dimensions, which is your projectile motion. And lastly, we have described about your uniform circular motion. That's it for this lesson. See you!